After exploring the reasons behind why Ethernet and why EPON, let's now take a closer look at their combination, EPON, or Ethernet Passive Optical Network. EPON is a popular choice for broadband network because it combines the reliability of Ethernet and the efficiency of passive optical networks. It offers seamless compatibility with Ethernet standards, scalability for growing network demands, cost effectiveness, and versatility across various deployment environments. Let's dive deeper into why EPON is such a widely adopted solution. EPON is built on Ethernet technology, which means it easily integrates with existing Ethernet-based networks and equipment. This native capability simplifies network management and minimizes capability issues. Since Ethernet is already widely used in enterprise and data center environments, implementing EPON does not require a steep learning curve or extensive retraining for network operators. One of EPON's strengths is its low-cost nature, stemming from the use of Ethernet and PON technologies. Its passive network architecture utilizes passive splitters to connect multiple end users without needing active electronics between the central office and the customers. This reduces both power and maintenance costs. Furthermore, EPON allows multiple customers to share a single fiber strand from the service provider, making it more cost efficient per user compared to point-to-point fiber solution. And the best part? Yes, EPON is highly scalable and can easily support high-speed service such as 10 gigabit per second without requiring major infrastructure upgrades. EPON is also flexible, offering both residential and business service over the same infrastructure, providing internet, video, and voice services. It can scale to accommodate growing numbers of users and increasing traffic demands without significant upgrades. Typically, EPON provides 1 gigabit per second symmetric speed, ideally for applications like HD video streaming, gaming, and VoIP. And with the advent of 10 gig EPON, it can now support even more data-intensive applications, making it future-proof solution. But with such high-speed data transmission requirements, do we foresee any challenges? Yes, indeed. At high speed, maintaining signal integrity becomes crucial due to noise, crosstalk, and attenuation that degrades the signal. The long distance and splitting architecture of EPON networks makes this change even more prominent. As you saw in our white equalization video, equalization techniques like continuous time linear equalizer (CTLE) and decision feedback equalizer (DFE) are essential for mitigating signal degradation. But they also add complexity, which can introduce new challenges. Power efficiency is another key challenge, especially in EPON, where power efficiency is another key challenge, especially in EPON, where SerDes circuits are used in endpoints devices that ON use. These devices are often deployed in home or remote locations, so power consumption directly impacts the operational cost. The challenge is designing a low-power SerDes that maintains high-speed data transmission without generating excessive heat or consuming too much energy. Techniques that TX-FFE, RX-CTOE, and RX-DFE are essential for signal integrity, but they increase power consumption. To manage this, adaptive power scaling, low power CMOS designs, and selective circuit activation during the idle period are important. But managing idle time brings its own set of challenges. When it comes to the idle and wake-up times of the CDR, EPON's variable traffic pattern and data burst can make this essentially tricky. CDR circuits need to quickly lock onto those data streams and handle jitter without introducing errors. Because EPON uses TDMA, time division multi-access, burst mode CDR is often required, which adds complexity compared to continuous mode. To address this, it's essential to use CDR architecture with fast lock time and robust jitter tolerance. But achieving this balance between stability, speed, and power consumption is no easy task. Lastly, there's the low jitter challenge in SerDes. High-frequency jitter can disrupt data integrity and cause big errors, which is especially critical in EPON, where data from multiple ONUs needs to be synchronized at the OLT. The SerDes circuit must handle both random and determinist jitter to ensure reliable data recovery and minimize big error rates. Achieving both low GTX jitter and high RX jitter tolerance is vital, but increases design complexity and impacts power efficiency. On the plus side, since EPON is Ethernet based, it benefits from Ethernet simple, well-understood protocols, which makes deployment and troubleshooting easier for service providers. This familiarity allows providers to use existing tools and techniques, reducing operational complexity and lowering network management cost. EPON also delivers reliable fiber-based connection with low latency, which is critical for real-time applications like video conferencing and online gaming. Its passive architecture increases resistance to power outages, as there are no active components between the provider and end user. However, achieving low latency in the design is a challenge, especially at the SerDes level. Every component in the SerDes, such as CDR, equalizer, and serializer, deserializer stages, adds to the overall latency. In EPON's shared architecture, additional latency can arise from synchronization and signal processing. To minimize the delay, we need to optimize such SerDes stage, possibly using customer digital designs to reduce the gate delays, but this often comes at the cost of increased power consumption over chip area. Finally, EPON is an open standard maintained by IEEE, ensuring broad capability across equipment from different manufacturers. This standardization offers operators more vendor choices, which help reduce cost and avoid the vendor lagging. In summary, EPON is chosen for its affordability, seamless integration with Ethernet networks, scalability, and ability to deliver high-speed, reliable broadband. Its Ethernet capability and passive architecture make it a practical solution for both residential and business networks. However, designing SerDes for EPON requires a careful balance between speed, power efficiency, jitter tolerance, and reliability. Taking this change requires innovative solutions to ensure robust, low-power performance in EPON's unique operation environment. We can dive deeper into EPON service design later. Just let me know if you'd like me to prepare the detailed design model for our next discussion. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and place your comments down below. Lastly, please share the video link with the people who may be benefiting.